Welcome to the 11th part of our word embedding series. Starting in this video, we'll begin exploring FastText embeddings. In this first FastText lecture, we'll focus on the Subword model. In the previous 8 videos, we explored word-to-vec embeddings. In this video, we'll first look at an overview of FastText, and then examine its core idea, the Subword model. Today, we'll discuss the paper titled Enriching Word Vectors with Subword Information, published in 2017 by Piotr Bojanowski and his colleagues at Facebook AI Research. The authors point out that existing word representations have limitations, especially for languages with large vocabularies and many rare words. To address this problem, the paper proposes a new approach based on the skipgram model, where each word is represented as a bag of character n-grams. In this approach, a vector representation is associated with each character n-gram, and each word is represented as the sum of these representations. This method is known to improve word representations, especially for morphologically rich languages, by incorporating character-level information. In this video, we won't cover the entire paper. Instead, we'll focus specifically on Section 3, which introduces the model. Now let's look at the problems with existing word embeddings. Word2Vec ignores the internal structure of words and treats each word as a completely independent unit. The first problem is morphological explosion. Languages such as Turkish, Finnish, and Korean can generate hundreds of word forms from a single root word. As a result, the model requires a huge vocabulary because every inflected form needs its own vector. The example below shows various inflected forms of the Finnish word talo, which means house. As you can see, a very large number of inflections exist. If all of these forms are treated as separate words, the model cannot efficiently share statistical information across related word forms. The second problem is the lack of shared morphological information. For example, run, running, and runner clearly share the same root, but Word2Vec trains them as completely independent vectors. Similarly, apple and apples differ by only one character and have almost the same meaning, but the model still treats them as entirely different words. The third problem is the well-known out-of-vocabulary or OOV problem. If a word that never appeared during training shows up at test time, the model has no way to represent it. The fourth problem is insufficient training for rare words. Words that appear only once or twice in the corpus do not receive enough statistical information, so their vectors are often poorly trained. FastText was proposed to solve these problems. Now, let's move on to the first core idea of FastText, the Subword model. The key idea behind the Subword model is to represent a word as a set of character n-grams. A set of character n-grams means all consecutive character sequences extracted from a word after adding boundary symbols. For example, suppose we decompose the word where into character n-grams with lengths from 3 to 6. Then we obtain the following set of subwords. Technically, character n-grams and subwords are not exactly the same thing, but in this lecture, we'll use the two terms interchangeably. First, we add boundary symbols to the word where. Next, we extract all character sequences of length 3. This gives us 5 subwords, as shown below. If we extract character sequences of length 4, we obtain 4 subwords. In the same way, we continue extracting sequences up to length 6. Altogether, we obtain 15 subwords. This entire collection is called the set of character n-grams. The authors chose an n-gram length range from 3 to 6 based on empirical observations. A minimum length of 3 ensures that each n-gram carries meaningful morphological information. This is because single characters or bigrams are usually too short to capture useful subword patterns. Setting the maximum length to 6 is mainly a practical design choice. Longer n-grams can capture more specific patterns, but they also dramatically increase the number of unique n-grams. That leads to higher memory usage and much sparser representations. Overall, the range from 3 to 6 captures the most useful linguistic patterns across many languages, including prefixes, suffixes, and root forms, while still keeping the model computationally efficient. Now let's see why FastText uses boundary symbols. Without boundary symbols, the n-gram her extracted from the bounded form of where would be identical to the standalone word her. In that case, the model would not be able to distinguish between the two. By introducing boundary symbols, FastText can clearly separate the n-grams of a complete word from those of its internal substrings. This allows the model to capture more precise morphological information. Next, let's look at the formula for the embedding vector of a target word. Here, W represents the target word. In the example on the left, W corresponds to the word where. And GW represents the set of all character n-grams belonging to the target word W. In this example, it corresponds to the 15 subwords extracted from the bounded form of where. Notice that the bounded form itself is also included. Z of G represents the embedding vector of each subword. These vectors are the trainable parameters of the FastText model. Finally, ZW represents the embedding vector of the target word. Using these symbols, ZW can be expressed as follows. That is, the word vector ZW can be represented as the sum of all subword vectors in GW. Now, let's look at a simple example. When we decompose the bounded word where, we obtain the 15 subwords shown in the columns of this table. This collection corresponds to GW. Each subword has its own embedding vector, which corresponds to ZG. Here we assume the embedding dimension is 4. If we add all the subword vectors together, we obtain the resulting vector Z of W, shown in the final column of this table. This is the final word representation for the word where. At this point, we now understand the basic idea behind FastText's subword model. However, you might still have a few questions. The first question is, doesn't simply summing n-gram vectors lose word order information? And the answer is yes, it does. Summing n-gram vectors removes explicit word order information, and this is a known limitation of FastText. However, this is an intentional design choice, not a flaw in the model. Because character n-grams already contain local sequential patterns, FastText can still capture a significant amount of morphological structure without explicitly modeling order. The subwords themselves do not form a global sequence. However, each subword still preserves local character order. For example, from the subword WHE, the model can capture the local pattern that the character E follows WH. As a result, FastText can capture local sequential patterns without explicitly modeling global order. The second question is, doesn't summing all the n-gram vectors cause the resulting vector to become too large and diverge? In practice, this usually does not become a serious problem. Although we are summing many vectors together, the number of n-grams per word is finite and depends only on the word length. So the total magnitude is naturally bounded. In addition, embedding vectors generally contain both positive and negative values. As a result, many components partially cancel each other out during summation. If you are still concerned about vector magnitude, there are standard solutions. For example, we can average the vectors instead of summing them, or we can apply L2 normalization after summation. Now let's compare the main differences between Word2Vec and FastText. Word2Vec is a word-level model, whereas FastText is a subword-level model. As we discussed earlier, Word2Vec assigns a single vector to each word. FastText, on the other hand, represents a word as a collection of character n-grams and defines the final word vector as the sum of those n-gram vectors. An important point is that n-gram vectors are shared across multiple words. In Word2Vec, the number of parameters scales with the vocabulary size because the model stores one vector per word. In FastText, the number of parameters scales with the hash bucket size because the model stores vectors for character n-grams instead. We'll discuss hash buckets in more detail in the next lecture. Another important difference is how the models handle out-of-vocabulary words. Word2Vec cannot represent words that never appeared during training. FastText, however, can still approximate out-of-vocabulary words using their character n-grams. There is also a major difference in how the models handle words that share the same root. In Word2Vec, words like run, runs, and running are treated as completely independent entries. By contrast, FastText allows these words to share subword information derived from the root word run, making their vectors more semantically related. Rare words are also handled differently. In Word2Vec, rare words receive very few parameter updates, which often leads to poor vector quality. FastText alleviates this problem because rare words can still benefit from shared subword information. Finally, Word2Vec does not explicitly leverage morphological structure. FastText, however, implicitly captures morphological information through character n-grams. Finally, let's write a simple Python function that decomposes a word into subwords. This function extracts character n-grams from the target word with lengths ranging from nmin to nmax. The code is very simple, so instead of explaining it line by line, let's just look at the results. If we decompose the word where, Using lengths from 3 to 6, we obtain the following set of subwords. Likewise, decomposing the word eating produces the following results. So far, we've explored FastText's subword model. In the next lecture, we'll explore hashing tricks and hash-based storage used to store subword vectors.